Alright, this is Algebra 1, Lesson 8-5. I'm whispering because I have to record this at roughly 12:49 in the morning, so I apologize that I'm not as enthusiastic or as loud as normal. Today's date is Tuesday, February 11th, 2020. We're talking about exponential and linear growth again, which was 8-1, but this time more advanced. So before we talk about our objective, let's see where we are in the unit guide. So we're down here in 8-5. So notice how it's the same title as 8-1, but a little bit harder now. We have one homework assignment tonight. Tomorrow's ski PE, so make sure you have all your stuff in. You know who you are. And then when we get back on Thursday, which is when our homework is due from tonight, we're going to be on lesson 8-6. So our objective today is to determine when an exponential growth equation catches up to a linear growth equation, because exponential is just faster, so it'll eventually catch up. It's just a matter of time as long as they're both positive, which they are for this entire unit so far. So as a review, what is linear? You're doing what with the common what to the initial amount, and it's very confusing what I'm asking here, but in this one I'm looking for an operation word, so add, multiply, subtract, divide, something like that. So linear is add. Linear growth is going to be add. The common, and then do you remember the word that we were using in 8-1? This is called the difference. So add the common difference to the initial amount. I'm not calling it the start now because I'm being more and more formal. So the initial amount, and then just add the difference, add the difference, add the difference over and over and over again. Exponential, you're not adding anymore. What operation are you doing? And you should probably already be writing this ahead of me, but it is multiply. So you keep multiplying, multiplying, multiplying by, what is this name called? We're calling it our factor. Or you can call it the base or the common ratio. There's a bunch of different terms we use, but generally speaking, it's your factor. And again, so start with your initial amount, multiply by the factor, multiply by the factor, multiply by the factor. Instead of adding the difference, it's this repetitive action that makes the difference between linear and exponential. All right, so we only have two examples, one example on the front, one example on the back. Let's talk about Ugo. He's doing some banking, or I guess in some investing. So he made two investments. Good job, Ugo. You have lots of money in the bank, it looks like. Investment A, you start off with $600. So by the end of the first year, you have $600, and every year after that, you get an additional $55. Not too bad. Investment B has a value of $500. Ooh, there's a typo here. It should be a money symbol here. So at the end of the first year, so just like at the end of the first year, and this one is increasing by 13%. So you can probably tell which one is linear and which one is exponential by now, and if not, that's okay. But if I ever see a static amount, that means I'm going to be dealing with a linear function there. If I ever see a percent, that means I'm going to be doing exponential. And that rule doesn't apply every single time, but if you do see a percent, yes, that is 100% of the time going to be exponential. But sometimes things will use the word like double or triple. That will also mean it's exponential. And we'll see that in example 2. So, Ugo, you're checking your investments only once a year at the end of the year. And the question is, what is the first year in which you are seeing that your investment in whatever B is exceeding the investment in A? So when does B catch up and then pass A? And it's kind of a hard question, like how are we going to approach this? And there's quite a few different ways to approach it. I'm going to do the most traditional approach, which is just making a table. So I'm going to have values of years, so year, and then I'm going to have, we'll say, investment A and investment B, and I can make this the entire table because I don't really need anything else. If you want a ruler, you can just sketch it though. I have technology, so I don't know how long the table is going to be, so I can always extend it later. But that's a good table for now. All right, so what is the information that we're given? And this is usually the trickiest part for me. I did all of the homework class, or tonight, I guess, like, I don't know, 20 minutes ago. And the one error that I made was just forgetting what the initial meant. So you don't start at year 0 like with computer science or anything like that. You start with year 1 in this problem because it says at the end of the first year. So on year 1, we start with $600. So on year 1, A starts at 600, and then same thing on year 1, we start with 500 for B. So I'm going to start at 500, and then I'm going to do some sort of operation. I'm going to increase by $55 per year. So increase in this case means plus symbol. So from here to get from year 1 to year 2, I'm going to add 55, so plus 55. And that's going to be 655. Nice and easy math there. What about what's happening with B? B is going to be multiplying by something because that's exponential, so times something. But what is that something that I multiply by? It increases by 13%. So we do have to do a bit of scratch work. So if you make your table the entire size of your notes, you can do it off to the side here. I do have this room over here, so I'm going to use it. What does 13% mean if I'm adding 13%? Well, again, I kind of use my, I don't remember what notes it was, if it was from 8.1 or 8.2, but I basically write down, wait, well, what percent was it? Yeah, 13%. 13%. And in order to convert it to a non-percent, I'm going to, it was 13.0%, I guess. Back here. 13% is the same thing as 13.0%, which is the same thing as 13.0000%. I can have as many zeros to the left and to the right of this as I want. For the sake of just showing you that there's a decimal there, I'm going to go 13.0%. So you can see the decimal move. In order to convert this into a decimal from a percent, I'm going to move the decimal 1 to the left, and this is now going to be 0.13 or 0.13 if you want to have that 0 in front, just to let you know there's a decimal there. So this is the percent that is being added to the original. Again, you always have to add this to 1, so we'll put in here add to the number 1, which means I'm really multiplying by 1 plus 1, or 1 plus 0.13, or 1.13. I'm going to have to multiply every single time, and it's not a very nice number, so we're going to have to use a calculator. So let's come up here and pull up our calculator, and we'll zoom in so we can actually see what's going on. There we are. Okay, so I'm going to say I have 500 times 1.13 and 565. That is actually a nice number. Cool. So 565. And then I check. All right, so on year 2, is B bigger? No, A is still bigger. All right, well, I'm going to do the same operation again. So I'm going to say, okay, plus 55, and I'm going to multiply by 1.13 and see what happens. So I can do this in my head. So if I add 55 twice, I'm really adding 110. So this should be 710 over here. 710, we're going 1 year into the future. So this is year 3 now. And times 1.13, so I can come back here. I don't have to type in 565 again. I can just type in AN, and as soon as I hit the letter S, it has the previous answer. That's what ANS stands for. You can say times 1.13. And now I'm going to get a decimal 638.45. 638.45. Okay, is B bigger yet? Nope. Okay, well, we're going to have to keep going again and again and again and again until we have our table all the way through. So one method that you could use is just have a bunch of these values. So let's maybe skip ahead a few. So I can say answer times 1.13 and 721. Notice I'm always doing the answer, even if I get a number that looks like this, I'm not going to round. I'm never, this is going to be 721.4. I'm going to round in my table, but I'm not going to round on my calculator. So 21.45. And I was multiplying by 1.13 again, and I'm going to multiply by 1.13. So ANS times 1.13, and I get 815. 815.24. I'm rounding in my table, again, not on the calculator, and we'll just do one more time just in case. So times 1.13. I'm guessing I'm somewhere around here. I'm probably going to be catching up, but I might have to do another value. We'll see. So let's do more. Answer times 1.13. I get 921.22. So 921.22. Cool. And now I'm just going to be adding 55 over and over again. You can use your calculator if you want, but I'm going to try to use my mental math. So I'm working on my smarts. Growth mindset says if you keep trying at something, you will eventually get better at it. So if you really don't like adding, the only way you're going to get better is by trying. So 765, add 55 again. That's going to be 820. Oh, really close. Look at that. I'm so close by this step. This is just a little bit less. We're trying to get this side more than this side. So by year 3, 4, by year 5, I'm really close. I'm going to guess, yeah, year 6 is going to be the answer. I knew I would have to extend this table. Oop, don't want to drag it. I just want to extend this table a little bit. I got really lucky. If you did it all the way out to time equals 10, then you did too much work. But notice here, if I say, okay, what was happening here? I was really adding 55. I think it's kind of repetitive at this point. You don't have to keep writing down plus 55. I'm doing it for the notes so you can see what's going on. And then this is going to be 875. Clearly, 921 is bigger than 875. So by the 6th year, Ugo, you now have more money in investment B. So I'll type out my answer as well. So by year 6, Ugo has more money in investment B. Cool. Technically, it's by the end of year 6, but that's being too formal. So by year 6, because that's what matched up there. Cool. So now I can show you maybe a cool shortcut that you could use, because the next example that I'm going to have is not a Khan Academy example. The Khan Academy always has it like within about, I don't know, 7 to 8 steps. You'll always be able to see which one is bigger. But the example that I'm going to give you next time on the backside is kind of big. You might have to go down like 30 of these table values. And if you're groaning at me, I'm sorry, but it's a fun problem. I want to see what's happening with these really, really powerful exponential equations. So, shortcut. I don't want to keep typing in times 1.13. So we learned the shortcut. If I want to say some initial value, we start at 500 again. So if I want to say some initial value, 500 times 1.13 times 1.13 times 1.13. There's a quicker way of doing that, and that's 500 times 1.13 to the power of x. Well, to the power of 3, rather, right? But if I want to be able to change this 3 to whatever, I guess I can just type over it. So I could say 1. That's when I do it just 1 times. So this 1 corresponds to this value after I've gone 1 year into the future. It doesn't mean I'm at year 1. That was my mistake on the problem. So when I type in a 1 into this function, that says I'm 1 year into the future, so I'm at year 2. So if I type in a 2, I go to 638.45. If I go to, so I can just click back up here and say 3 goes to 71, 71, etc., etc. So that's your shortcut using your equation like that. And you can also use the equation over here, which is 600 plus, instead of multiplying, and how much am I adding each time? 55x. So this x could be like times 1, 2, 3, 4, 5. Notice that all of those match up with the values that we had right here. Again, this is 5 years into the future. So while that shortcut is nice, there is an even faster shortcut. I'm all about like learning the shortcuts as long as you really understand them. If you don't understand them, do it the long way. It's still correct. You make sure that you have that understanding. But here's the shortest of the shortcuts. Are you ready for this? What if I did this? So if I create my equation, 500 times 1.13, and actually leave it as x, and just hit enter, it says, yeah, I don't like that. I don't know what x is. Just bear with me for now. Didn't mean to click on that. And the second equation, I have an initial value of 600, and I'm going to be adding 55x. Again, it says, hey, what is x? But now I'm going to say, hey, x is 1 year in the future. Check out these values up here, 565, 655, 565, 655. That's what I have right there. What if I change x to 2, to 3, to 4, to 5? Oh, now this one is bigger than this one. So 5 years into the future, always just add 1. If you always just add 1 to this, that will be the answer. So the answer here was 6 because 1 plus 5 is 6, and that means that this value is higher than that value. So that is a really, really good time saver. But you have to know where these equations come from. And we've seen table values before. We've seen so it's not that much of a stretch to figure out where these equations come from. But I can move this down, or you can write underneath this. If you want to know where these equations come from, it's always going to be start for a linear. It's going to be start plus difference. I'm going to abbreviate. I'm going to say difference like that. Difference, our difference in this case was 55 times x. So in this case, our equation, I can do it below this, was our start was 600, 600 plus the difference was 55, then times x. So that was the equation that I typed in over here, 600 plus 55x, 600 plus 55x. Over here, the equation is start, I guess I should be using the word initial, I'm so used to using the word start, so start times the factor to the power of x. And that's why we did start of 500. Looking at our equation, 500 times 1.13 to the power of x. That's where the equations come from. It's really cool now, like by this point in our unit, we're able to relate the table values. So this table of adding 55, or multiplying and multiplying, we can relate the table, the graph from yesterday, the equation, all of them together, and see the difference between linear and exponential. It's kind of this really cool, powerful conceptual understanding. So again, I'll repeat, you don't have to use a shortcut, but it is really, really nice to know. Have all that interconnected math happening in your head. Let's go ahead and work on example number 2. So I am I'm wondering if Charles is playing this video on his computer in front of the class. If you are, Charles, can you pause it and let everyone try a crack at it for 2 minutes? It doesn't have to be that long, just enough to where people are kind of understanding what to do. And if you are all just watching this individually, then here we go, because you've unpaused the video. So we're making another table. And now we're talking about Jade, and she's trying to feed her hungry, I assume, village. You've probably heard of this problem before, where you have like a chessboard where each square you get double the amount of grains of rice. It's very similar to that. It's just a slight twist, because whereas on the chessboard I can add up all the squares, I'm not really adding up anything. I'm just purely doubling it. I'm not adding like 1 plus 2 plus 4 plus 8. I'm just saying, yeah, just double it, and that is the amount of rice. So a slight twist. If none of that makes sense, then ignore me. Here we go with the math. So let's see, our units are days, so each day, so my left-hand column is going to be day, my next column is going to be deal 1, and my right column is going to be deal 2. Let's go ahead and mark our, so this is going to be a big table, I'm warning you. Sure, let's make it the entire, ooh, I don't want that color, the entire table. That looks sufficient. Okay, so what is happening in our problem? On day 1, she starts from 0 rice, so by the end of the first day, I'm reading here, so by the end of the first day, so on day 1, she'll have 1,000 grains of rice. 1,000. And if you want to put a comma there, you can. I don't normally do that though. So that's what's happening there. And then each day, so it's saying each day it increases by 1,000. So on day 2, you're going to have another 1,000, 2,000. And while it's just grains of rice, that's still a bit of rice. I'm just curious now, how much or how many grains of rice in a typical bowl of rice? I don't know. Okay, so if you're making a bowl of rice, it's 3,000 grains. So sorry, you're not going to be able to feed very many mouths today. I didn't realize how big a bowl of rice was, 3,000 grains. So on day 3, it's going up by another 1,000, 3,000, etc., etc., etc. What about for 2? What's deal 2? So Jade, you get to double the amount of rice. So at the end of the first day, I'm just reading right here, at the end of the first day, you'll have 2 grains of rice. So 2, and that's going to double. That's going to go to 4, then it's going to double, goes to 8. And just to make sure everyone sees the pattern, to get from here to here, I am multiplying by 2, multiplying by 2, etc., etc. I'm going to stop writing that. To get from here to here, I'm adding 1,000. I am adding 1,000. So this is the linear column, this is the exponential column. We're trying to figure out when does this number catch up to this number. And you, by all means, can continue the table. The table is going to be probably even longer than this. You might have to come over here to the right-hand side to continue out your table. But I don't want to do that. I want to use a shortcut. So how do I use a shortcut? I come back over here and come back to our calculator. I'm going to go ahead and clear everything. Clear all. I want to figure out the function that does this for me. So the function that does this, I know that I'm always going to do, you can write it down again if you want, it's always the initial, I'm going to call it the start because it's a smaller word, start, and then it's going to be plus your difference, and that's going to be times your x. So what did we start with? I'm going to say, we could do it slightly different. We could say that we start with the 0. On day 0, we can go all the way back here to 0, 0, 1. We could go backwards in this table, and that would make the equation slightly easier. I don't know if that's going to confuse people, though, so I'm just going to say we started with 1,000, and then we'll always have to add 1 to this. Just like I said in the last problem, I'll be consistent. Sorry, we started with 1,000. And what was our difference? Our difference, we're increasing 1,000 each time, plus 1,000 and x. So there's our equation there. Over here, my start now is 2. So let me write down my equation first. It's going to be the initial value, or the start, times your factor to the power of x. So this one's going to be start of 2 times, and then the factor again is 2 to the power of x. If I type these equations in and then start plugging in values of x, I'll eventually see that this one gets bigger than this one. I'll type this linear one in first. Can you do? Oh, you can't. Okay. I was thinking that's kind of like the other calculator. So 1,000 plus 1,000x. And the next equation is 2 times 2 to the power of x. And let's say x is equal to 1. So x is equal to 1 means we are 1 day into the future from 1. And notice it's 2004, 2000, and then number 4. So 2000 and then number 4. This is 1 day into the future, so it's day 2. And if I do x equals 2, that's 2 days in the future, which means I'm at day 3. On day 3, I have 3,000. Day 3, I have 3,000, and I have 8. So now I'm just going to keep going bigger and bigger. I can even just guess 10. Okay, I'm trying to make sure that the bottom number is bigger than the top number. Nope, keep going. 15. Ooh, 15. Now the bottom number is bigger, so it's less than 15. 14. 13. Ooh, 13 is real close. 12. Okay, so 12, the linear function is bigger, which is not what we wanted, but now at 13, it is bigger. And the cool thing about this little shortcut here is when I go to 12, I can actually say, okay, 12 days into the future should be day 13. So I'm going to do, the way that mathematicians write it down is they say dot, 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 your ellipses, if you don't know that word. Now you know it, it's called ellipses. This is a vertical ellipses. And now I'm going to go jump down here to day 13, aka 12 days in the future. And that will be the value of 13,000. 13,000. and 8,192, 8,192. And by day 14, if I come down here and do 13 days in the future, I have 14,000, 14,000, and 16,348. 16,348. And we can see now that this side is bigger than this by day number 14. So I guess I lied to us when I said that these need to be all the way down. I can grab this and make it slightly shorter, and then I can answer the question. Always answer the question. So what is the question asking? The question is asking the minimum number of days Jade should wait until deal 2 exceeds the amount of rice from deal 1. So finally deal 2 has exceeded the amount of rice from deal 1. So Jade needs to wait 14 days before the grains of rice from deal 2 exceeds the grains of rice from deal 1. And that's a very long-winded way of saying it, but the answer is 14. That's the main thing that you need to take away from that. Cool, so there was lots and lots of math happening today. That's all I have for you guys. Good luck on the homework. I'll see you guys on Wednesday for Ski PE.